Hey there, this is Seth Schaefer from Team Jessica's Robotics, and in today's video I want to talk about gears. Why gears? Well, I just recently added some gear products to my web store, but aside from that, gears are one of the most fundamental engineering tools that we have to transmit torque from a motor into some kind of mechanism, wheels, or other systems inside of a robot or other kind of hobby projects. So I feel that it's an important subject to talk about, and something that's often misunderstood by a lot of people, especially when it comes to 3D printing gears. So I want to talk today about a bunch of different topics, including how to best choose a gear's tooth size and other factors that affect what choice of gear you would use, the different materials you can use for gears, both 3D printed and otherwise, what is the best way to utilize these materials and attach them to motors in different ways, especially in the context of 3D printed gears where that can be a real challenge. I also want to talk about the ways that I've used them in past projects of mine and other robots like you can see behind me, and I'll show different examples of how they're used all over the place. I also want to talk about all the different types of gears that there are, the ones that are easy to manufacture, or easy to 3D print, or cheaper, and where you can get those. Lastly, I'll also quickly go through how you can use a CAD tool like Fusion 360 to easily design custom 3D printed gears so that you can integrate them into your own custom projects. So today I want to talk mainly about applications of gears and how you can actually use them. If you want to learn more about the theory of how gear teeth are designed and all of that sort of stuff, I'll link a couple videos below with some really nice overviews of that. Let's go back a second though. What exactly are gears for? Well, gears are for a compact way to transmit torque from a motor into another system. For example, on the drivetrain of a bot-like division, you'll see that there is a pinion gear mounted to a motor, just like you see here. And there is also a gear on the wheel, like you see here. And these can mesh together so that when the motor turns, the wheel turns with it. However, you'll notice the gear on the wheel is much bigger, and the speed at which this will turn is about 5 times slower than the speed this one will turn, because that's the difference in the number of teeth on those gears. In other words, that is the gear ratio. So if you have a gear with, say, 11 teeth, like I have here, and a gear with, say, 55 teeth, like you have here, then for every single rotation of the 11-tooth gear, you'll get 1/5 of a rotation out of this gear, but it will transmit 5 times as much torque into the larger gear. And the same thing works in reverse. If you were to drive a large gear and then turn a small gear, every one rotation of this larger gear would result in the smaller gear turning 5 times with 1/5 of the torque. Now, there are plenty of cases where gears are linked together with more than just one big gear and one small gear. You'll sometimes see that there's a bunch of gears in a chain together. In that case, the only thing that matters if the gears are all linked together is whichever gear is being driven, the size of that gear, and whichever gear has whatever you're powering on it, the size of that one. All of the gears in between, their tooth counts don't matter whatsoever. There are also a ton of different types of gears. Some of them are easier to manufacture than others. For instance, the simplest type of gear is, of course, a straight tooth spur gear, which is basically your standard gear. This is an example of a steel spur gear. It has steel teeth. Here is a matching steel spur gear, and you can see that they mesh together quite nicely and roll really easily together. No problems there. You can also get what are called ring gears, which are basically just an internal toothed gear, like this, which is the same exact tooth profile, and I'll show you later how you can generate these in CAD. A similar but less commonly used type of gear, which I used on my 3-pound robot mini mulcher, is called a helical gear. The helical gear is basically just a spiralized spur gear. So you'll see that the teeth kind of twist around. This is the matching pinion, and you can see they mesh together nicely. Like with spur gears, you don't actually need to set exactly where along the face of the gears that they mesh, so you can kind of slide these in and out a bit. However, you will have some force trying to push upwards or downwards along the shaft as these rotate because of the spiral pattern. You can see here how I implemented this in Mini Mulcher. I have a weapon motor deep inside, mounted to the bottom here, and that turns the small gear, which then in turn spins the big gear, spinning the weapon. It's nice and compact, and you can 3D print both gears pretty easily. However, these are quite a bit more expensive to manufacture in metal, so it's less common to see them around. One interesting variation on the helical gear is called a herringbone gear. A herringbone gear has a pattern that's kind of like a chevron shape or a herringbone shape. This one is not symmetrical, but you more often see symmetrical ones. I made them not symmetrical in this case so I could drive a wheel on one side and have the motor shaft on the other side without potentially rubbing against the wheel when it's mounted to this face. I also used herringbone gears in my 12-pound robot Draconid as part of the drivetrain solution. You can see here there is a clear 3D printed nylon gear on the motor and a blue PETG printed gear which has been damaged slightly as an intermediate gear here, and you can see I also belted to the front and back wheels. This system worked pretty well, though it's a little bit complicated. Within the same type of gear, you can pretty much make any size of gear tooth that you can think of. From a really, really big thing like this, which is probably a module 2 or 2.5, to a small tooth like this, which is only a module 0.5. There are two different ways to describe the size of a tooth on a gear. For spur gears, which I'll basically talk about for the rest of this video because most of the same rules apply to everything else, you essentially are just using a number called the pitch or the module. A pitch is the imperial measurement, and it describes how many teeth there are for every inch of diameter. So a larger number means smaller teeth. For instance, a 32 pitch gear, which is really common, is about equivalent to a 0.8 module gear. So for a 0.8 module gear, the ratio between the pitch diameter and number of teeth is 0.8. For a 1 module gear, the ratio between the pitch diameter and number of teeth is 1. This is what a module 1 gear looks like. This has 12 teeth and a pitch diameter of 12 millimeters. One other number that's sometimes used to describe gear teeth is the pressure angle, but for almost any gear out there, the pressure angle is 20 degrees, so sometimes it's not even listed and it's not really worth worrying about. If you want to buy a gear off the shelf and then 3D print a gear to match, the only thing you really need to make sure of is that the pressure angle and the pitch or module are the same, which is really easy when you're designing a fully custom gear. The tooth counts can be basically anything and will be decided based on the gear ratio you need to suit your system. If you want to know what kind of gear ratio is best to suit your system, there's tons of resources for that too. If you're looking at a drivetrain, I have my own video, which I'll link down below, which shows exactly how to determine the best gear ratio for a drivetrain in a robot. One other thing to keep in mind that doesn't affect the compatibility of gears but it's useful when you're designing is the face width, which is essentially just the width of the teeth that you can use on the gear. On a gear like this, where the whole thing is teeth, it's literally just the width of the gear. Here it's about 1/4 inch. In some cases, however, you might have set screws inside your gear, like you see here. The set screws in this gear make it so that even though this gear is 18 millimeters long, there's only 12 millimeters of usable width on this because the set screws need to be accessible. So when you're using a gear like this, you can match it to a gear that's 12 millimeters or so, or if you want the gear to stick out on one side, you could use wider, but you have to make sure that they align correctly. Really briefly, I'll also talk about ring gears and rack gears. A ring gear like this is basically just an internally toothed gear, but it works essentially exactly the same as a regular spur gear. The number of teeth on this versus the number of teeth on the motor driving it determine how fast that it turns, just like with regular circular gears where the teeth on the outside. There are also, however, rack gears. Rack gears are interesting because they are straight lines with teeth carved into them. A rack gear is actually designed to transmit rotary motion into linear motion. It's used a lot on CNC machines where you need to have a ton of travel where the motor travels with the gantry and the gear spinning on it to climb its way along the sides. Now, rack gears work a little differently because they're not spinning, obviously. So for a rack gear, you're essentially doing the same kind of calculation as you would for a wheel to figure out what the linear speed is from that wheel based on the rotations of the wheel per minute, or RPM. And for that, you're just going to use the pitch diameter rather than the outside diameter of the teeth of the gear. So now we know basically if you were to buy a gear and want to 3D print a gear, how you can make sure that those work together. And if you just want to 3D print two different gears, you can basically do anything with design freedom. So now let's talk about how you would actually decide on what size teeth you actually want for an application. Well, honestly, there are some mathematical calculators you could look up if you Google around for a little bit, but a lot of it, like with a lot of engineering stuff, honestly kind of comes down to feel, especially in the combat robotics world where everything's so unpredictable. Or, of course, you can just look at what other people have done successfully. On Division, for instance, I use a steel pinion gear on my motor shaft, and I drive a wheel using a 3D printed nylon or carbon fiber nylon gear. Here I'm using a ratio where this wheel has a 48 tooth gear on it, and the motor has an 11 tooth gear on it, and that gives me a good enough ratio to drive this bot around perfectly fine because I'm using a really powerful motor. However, most smaller robots will use a planetary gearbox. Planetary gearboxes, like this one, are able to put a bunch of gears in a tiny package. If you want me to do a separate video on this, make sure to comment down below to let me know. Planetary gearboxes basically use a clever arrangement of gears in a smaller package with a ring gear on the outside to make it so you can get a really high ratio in a really small package. This is a 23-to-1 reduction just within this little metal cylinder here. So when you're designing a system, the first thing you need to keep in mind is basically what is the total reduction that you want. Also, if you're trying to drive a wheel or an arm especially, something that's going to require a lot of torque, you typically, if you're going to use a planetary gearbox, don't want to directly drive the high torque thing on the shaft of the gearbox, because oftentimes those have small bearings and they're easy to break, and they won't really deal with off-axis loads very well. Alright, next, let's talk about what materials are ideal for different types of gears. So I'm mainly, again, going to focus on spur gears, but there are tons of different applications for spur gears that lend themselves better to one material or another. There are sort of 3 different metals that are used primarily for gears, and in industrial applications, there are a couple different plastics that are often used, but I'll also talk about the different 3D printable materials that we might use. So first off, for metal, there's basically 3: steel, aluminum, and brass. Both steel and brass are extremely dense metals. They are about 9 times as dense as plastic or 3 times as dense as aluminum. Steel gears, though, are often case hardened or heat treated to make them extra hard, like the gears that I have custom made that I sell on my website for Division's drivetrain. These will typically last far longer in an industrial application than a brass gear would. When you're designing for gears with 3D printing, I would prefer not to use a fiber-filled material because you generally have a rougher surface finish, and because you're dealing with a rolling or a sliding contact with the gears, that will actually degrade their performance and cause them to wear excessively over time. Here in Minimulture, the gears are printed out of Talon Alloy 910 nylon. This is probably the best all-around material that you can use for gears if your printer can handle it. In a lot of cases, however, if you have a cheaper printer that can't print high-temp materials or engineering filaments like nylon, you can get away with PETG gears like these. I prefer PETG to PLA for this application because it's a higher temperature resistance material, and I've melted PLA gears in higher speed applications before. They generally just kind of suck. So PLA has a higher friction coefficient than PETG by a tiny little bit, but both of those have a higher coefficient of friction than nylon, so nylon is definitely preferable if you can use it. Now, if 2 plastic gears are rubbing together, that's where you really need to be concerned about the frictional coefficient, but if you have one steel gear or brass or aluminum gear being driven by a 3D printed gear or vice versa, generally speaking, any plastic, even a carbon fiber or glass filled plastic, will be fine because that will wear a lot slower than the metal. Now I'm going to talk about how to actually drive things with the gears. In other words, how you can attach the gear to your motor shaft and how you can attach your gear to whatever else it's driving. So there are kind of 4 main ways that we tend to drive gears with a motor shaft. There are a couple that are only really suitable for metal gears, and then a couple that are suitable for metal or 3D printed gears. The first way is press fit. This is by far the least common one that you'll see, and it really only works with metal because plastic has a tendency to creep over time. So if you press a plastic gear onto a shaft and it seems like it's working at first, it will loosen up over time. This is a module 0.5 pinion gear that's used in my Dartbox gearboxes, which is a 2mm bore pressed onto a 2mm shaft. The bore is actually undersized by a few hundredths of a millimeter to make it so that it actually makes the gear expand slightly, and the spring is basically compressed onto the shaft all the time, which allows it to transfer torque really efficiently without needing a set screw or even Loctite or anything. The second and most common way in engineering that you would typically do this is with set screws. Set screws bite onto a flat on a motor shaft, or you can grind one onto the motor shaft if it's a smooth shaft, and that allows you to transfer torque really well. The next common way for driving a gear, if you're using a 3D printed gear, would be to use some kind of a set screwed hub. Here I have a custom machined aluminum hub with set screws that go on either side of it that allow me to secure it to the shaft, and then there's an imprint of the hub in the gear. You'll often see this with a hex-shaped hub like the BaneBot's T40 hub, and I'll be selling some wheel hubs that have a hex-shaped 12mm hex on my web store at some point in the next month or so once they're machined. Another thing you can do if you have a much larger motor, like I have on my 12-pound robot here, is you might be able to just bolt the gear straight to the motor face with some screws. Most of the smaller motors you'll see in like 3-pound bots, though, won't have a large enough face to even put screw holes in, or won't come with screw holes to do this. There are some clever tricks that you can use in some cases that are similar to using a hub. In Mini Mulcher, for instance, the shaft on my motor is a threaded M5 shaft, and I actually used an M5 threaded hexagonal lock nut that is clamped onto the shaft by just screwing it as tight as possible. And that hex shape has been printed into the gear so that it turns with the shaft quite nicely. This works best in an application where it's only spinning one direction, so you can make sure that it's always tightening though, because if it were to have to spin with a lot of torque in the other direction, it might just loosen that thread, and that wouldn't work out very well. Now, to secure a gear to the thing actually driving with it, there's kind of two different ways to do this, and this applies to basically any kind of power transmission with rotational motion. You can either use a live shaft, in which case you're basically doing all of the things that I just described for motors, because the shaft is spinning with the gear, or you can use a dead shaft, where you basically put bearings or bushing inside of the hub of the gear, and it spins on a non-rotating shaft. This is a good example of a dead shaft setup. I have a shoulder bolt through the center of this aluminum machined hub with bearings pressed into it, and that allows this weapon to spin super nice and freely, which is quite nice. And I've got a gear kind of stretched around that hub, which has an eccentric shape so that the gear will have to turn with the hub. Okay, so you've decided you want to use gears in your design. How do you actually put them into your CAD model? Well, the first place to look is going to be different manufacturers' websites. So here's a look at ServoCity, and you can see they've got a ton of motion components, including gears, and they include CAD models for all of their stuff. You can see how much it costs to buy all these metal gears and integrate them into your design, etc., etc. They've got plastic ones here too, but if you're 3D printing things, then obviously you don't need to buy plastic gear. Next, we've got Mizumi. This is one of the engineering suppliers that I use a lot. They are pretty expensive, but again, they have CAD models for all their gears. You can always just take a CAD model for an existing gear and modify it. They have like a bajillion options for everything. You could also try McMaster-Carr. Again, they have CAD models for basically every single thing in their catalog. And if you look at, whatever type of gear that you need with whatever gear pitch and what have you, you can find gears that match and then modify them for your design, etc. The next option, which is better option generally if you're 3D printing the gear, is to use a gear generator, which you can usually find within your different CAD programs that you're using. Really quickly, I just want to go over how you can use gears in a CAD design for your own kind of robot if you want to 3D print them or what have you, or just design a gear that interfaces with an existing one you can purchase. So for that, in Fusion 360, which I'm in here, you can use a gear generator that's built into Fusion for free. If you just go to Scripts and Add-ins, scroll the way down, go to Spur Gear, type in all the different numbers, hit OK, and then it generates a gear for you, just like I've already done here. Another thing that you can do is use some other free plugins that you can install. So if you go to Add-ins, Fusion 360 App Store, the two that I use are FM gears, which also lets you generate straight-tooth spur gears, but also internal and rack gears for those. And then the other one is the Helical gear generator. I personally use this one, which is also free, download and install. To use either of those plugins in Fusion, if you go to the solid modeling environment and then go down under create, you'll see them at the bottom here. So if I select Helical gear, just like before, you type in the numbers for the different features you want and then hit OK, and boom, you end up with a perfectly generated gear. And now you can add a bore or whatever other features you want to it, just like you would do to modify something that you were in the process of creating yourself. So if I want to add like a 12mm bore, I can just do that. And you can do whatever else you need to modify this to make it work with your design. Alrighty, well this has been a pretty long video. For the 17 of you still watching, thanks for sticking around. If you like this video, make sure to click like. If you want to see more videos like this, make sure to subscribe and click the bell icon to be notified when they come up. Also, if you want to support what I do, it would be great if you could buy the gears that I mentioned at the start of this video from my web store, which is linked in the description down below. I'll also have a bunch of links down below to a bunch of the places that I talked about where you can buy gears, and a few other videos that might be worth watching if you're interested in going even deeper, because honestly, like in every other engineering subject, there is almost infinite depth to this subject, and there's tons more than I could possibly have hoped to fit in a video that was less than an hour long. I left out tons of different kinds of gears, like miter gears, bevel gears, and worm gears that allow you to drive things at a right angle, and a few other things that I just didn't feel like was worth getting into in this one. Again, let me know in the comments if you'd like to see a video on planetary gearboxes or other forms of power transmission in the future. And yeah, that's all I've got. Bye!